there any questions? No? Okay, I did, I think at the end of last lecture, I did example 7.3. 7.13, which has this thing with the square distribution. That's the function omega looks like this. Okay, and then mentioned that there could be something wrong with that formula in the end of their example. Actually, it's not wrong, it's because omega is defined differently. For low pass filter, bandwidth is defined to be, the bandwidth is defined with this as the omega. But if you have a band pass filter, like in the example over there, in the example, this thing over here is defined as omega. Okay, so there was this little blackout region and this little blackout region. But then omega is defined differently for this case A and case C. That's why there's a factor of 2 difference in the last equation. Okay, because omega is defined to be the entire width of the base of the triangle, whereas omega is defined to be half the width of the base of the triangle. Okay? So, sorry for the confusion. Because for this thing, I think we get the fact that omega is equal to 0.7764 pi. So this thing we get omega equal to 1.5528 pi. Okay, and the difference comes from the different definition of omega. Okay, let's go to section 7.3 and discuss some examples from there. And essentially, as I told you before, when you have a linear time invariant system, you know that if you have a single frequency going in, the output is given by h of omega e to the j omega. Okay? Because this is a frequency domain system, because before we reached there, we actually had the phasor form. That if you have, say, a phasor quantity like f e to the j omega t, okay, then the output would be something like real part of f times h of omega e to the j omega t. And from this diagram, you can actually get the above diagram, because the bottom diagram means that it's valid for all t, and this thing is going round and round in a circle, so you can take out the real part and get the above diagram. And hence, if this is true, this must be true. And if that is true, then it's true for Fourier transforms. So if we have a Fourier transform signal which is a sum of all different harmonics, this is called a harmonic. You can write a Fourier transform as such. Okay, and if this is the input to the LTI system, by the logic of this diagram, if every harmonic gives this output, then the sum of this harmonic will give an output that looks something like this. Just by the principle of linear superposition, because an integral is a summation of some sort. Okay, integration is a summation of some sort, and hence the output should look something like this. So are there any questions regarding this diagram? That once you know the input, you know the frequency response of the transfer function of this linear time invariant system, you can find the output as such. Yes?
D omega.
What?
It's D omega.
Oh yes, d omega, right. d omega. Okay, d omega. Okay. Yes, you have a question? Okay, thank you. So this is just linearity. Okay, principle of linear superposition. When it's valid for one frequency, it's valid for sums of frequencies. Okay? So let's do example 7.15 of the textbook. Okay? You're given that h of omega is equal to 1 plus j of omega. And then you're given the fact that the input f of t is equal to e to the minus t u of t.